frazzled as the semester goes on. Can we just resubmit the ones we got 100% right? You mean the ones that you didn't get 100% right? Yeah, I suppose. If you only got a couple points where you, or if you only had a couple problems where you missed them, yeah, there's no need to resubmit the problems that you got full points on. That's a good question. That's a good point. Any further questions? Wish I got to class early so I could ask y'all if y'all did anything cool over your weekend, but instead we are late, so I'm just gonna dive right in. So what did we go over last time? Last time we finished off strong induction and we started modular arithmetic. We started with the division algorithm. Now, could someone remind me, that was not so bad handwriting actually. Could someone remind me what the division algorithm says? Yeah, exactly. The division algorithm says, well, I want to think about A divided by D. But in the integers, we can't divide. We can't necessarily divide. So our best replacement is to divide with remainder. Namely, A is equal to dq plus r, where what's the condition on r? And this is an important thing, where r is in what range? R must be positive, and R can be 0, actually. So we want 0 less than or equal to R less than D, exactly. So we want to keep track, we want to allow R to possibly be 0, because it actually is possible sometimes for A to be divided by D, or namely for A to be a multiple of D, right? If I think about 8 divided by 4, then the division algorithm would tell me that 8 is equal to 2 times 4 plus 0. I want to keep track of a remainder 0 in this case. So we comfortable with the division algorithm more or less? Sounds like yes, because I got a lot of good answers in the chat. Okay, so a very important point that we're going to spend a good chunk of today on is the following definition. So let's say, once again, we're in the division algorithm situation. So A is equal to dq plus r. Then we make the following definition. Then r is going to be equal to A mod d. So mod d is essentially a function. So in other words, mod d is a function that goes from the set of integers to the set of integers between 0 less than d. So 0, 1, 2, all the way up to d minus 1. And so how does mod d act on an integer? Well, you send a to the r part of a, so it gets sent to r where a is equal to dq plus r. So essentially mod d is the function that says write your number using the division algorithm and then only remember the r part, only remember the remainder. So for instance, what's 7 mod 3? Yeah, this is just 1. What about negative 100 mod 7? That's kind of a harder one. Is it 5? Let's kind of go through this. So negative 100 mod 7, I need to write negative 100 is equal to something times 7. In this case, probably, let me think. So 70, 77, this is 11 times it. Then we get to 84, then we get to 91, then we get to 90 plus 7, 91, 98. Then we get to 105. So we get, so I can get to negative 105 by multiplying by negative 15. So 7 times negative 15 plus 5. And so y'all are, of course, correct. Right. I mean, these are negatives, right? Did I do this correctly? I think I did. Oh, yeah, I'm sorry. You can't see this. Boy, rough day today, huh? Is this back of the envelope calculation reasonable? So mod d is a function that I can apply to the integers, and then I land in this set between 0 and d minus 1. Any questions here? Should I do another example? I should do another example. Okay. Then I'm going to let y'all pick the numbers. What is going to be a? Someone give me a number for a that's reasonable and not too crazy. Let's do one example where a is positive and another example where a is negative. A is what? 27. Okay, great. A is equal to 27. And then what should my divisor d be equal to? 4. Perfect. So what I'm computing is 27 mod 4. So what this tells me to do is I use the division algorithm to rewrite 27 with respect to 4. So 27 is equal to, well, how do I, in multiples of 4, what can I get to? 4 divides 20, 4 divides 24. So 6 times 4, this chunk is equal to 24. And then the remainder, the stuff that's left over, is a 3. And indeed, this 3 satisfies the requirements because it's less than or it's greater than or equal to 0 and less than 4. So this is how I would write 27 with respect to 4 using the division algorithm. And the remainder is 3. So that's just what this function does to 27. It sends it to 3. Let's do the negative. If I look at negative 27 mod 4, well, I have the same idea. I want to expand out negative 27 using the division algorithm with respect to 4. So negative 27 is equal to, now instead of, I want to kind of draw a picture again. This is kind of messy work, but sorry, you know. Here's 24, here's 27. So I added 3 to get between 24 and 27. Now down on the negative end, I've got a negative 27, I've got a negative 24, and I've got over here a negative 28. The point is, I always need my remainder to be a positive number. So when I'm thinking about negative numbers, I think that I need to go past the negative 27 and then add 1. So in this case, negative 27 is equal to negative 7 times 4. So this is negative 28, and then I add 1. I always am going to be adding something. If I'm doing mod 4, my remainder always needs to be either 0, 1, 2, or 3. No, nothing else will do. Should I do yet another example, or is this kind of making us a little more comfortable with this procedure? I'm happy to do another example. It's kind of fun. Okay, well, no one spoke up. So what we're next going to do is discuss modular arithmetic, which is essentially arithmetic where you are always working with modular arithmetic. So here is the kind of idea. Sometimes we only care about a number up to its remainder. For instance, if I say, what time will it be in 176 hours? The point is, I don't actually, the only information that's relevant perhaps to me is whether I can drink tea in 176 hours. And so I'm not asking for the specifics of what time it is. I'm only caring about what number is on the clock. Namely, I only care modulo 12, or if I'm European, mod 24. Right? Like for instance, we can do a more basic example. When I say, what time will it be in 25 hours? Something that you all immediately know is that it will be 10:27 or 37, right? In 25 hours, the time will be 10:37. But this is already us doing modular arithmetic, because the only, well, maybe I should be more particular about just doing hours, for instance. But if I say, what time will it be 26 hours from 9 a.m. today, the answer is it will be 11 a.m. So this is the same thing as doing 9 plus 26 mod 12. And we can actually calculate this. 9 plus 26, this is the same thing as what, 35? And now when I think about modulo 12, I'm essentially doing, what is 35 mod 12? This is equal to, expand using the division algorithm. 35 is equal to 24, well, 2 times 12 plus 11. And this remainder, 11, is the correct time. That will be 26 hours from 9 a.m. today. This is maybe a little sketchy, but does this example kind of make sense for some real world problems where modular arithmetic, or only considering remainder, is the reasonable thing to do? Another reasonable example is, what day of the week will it be in 365 days? Right? Here, the right way to approach this problem isn't to have a list of all of the days ever, right? We don't want to think of days as integers. we only want to think of days as being the same as numbers 0 through 6, namely 0 is Sunday, I guess. 1 is Monday. 2 is Tuesday. 3 is Wednesday. 4 is Thursday. 5 is Friday. 6 is Saturday. Right? So this is a way that I can set up the days of the week to be in bijection with the possible remainders mod 7. Maybe instead of asking something like 360, I mean, we can do 365, right? So essentially today is Monday. So I'm asking about 1 plus 365 mod 7. Let's actually do this one. So 366. Can someone with their pocket calculator tell me what 366 divided by 7 is? So I do the division algorithm. I do 366 is equal to, perfect. So I do 52 times 7 plus 2, apparently. And I should check this. 7, so I get a 14 for 1, and then 7 times 5 is 35, so I get a 36. 364 plus 2. Oh, very nice. So the remainder is 2, which tells me in 365 days, it'll be Tuesday. That's quite nice. It's kind of a very explicit example where you see there are reasonable cases where we only care about the remainders and not about the full sum. So the point is that maybe a more reasonable thing to ask you is if it is, maybe we should do some more small case examples. What day of if it's Monday today, so we're on day 1, what day will it be in 7 days? Well, that should be 1 plus 7 modulo 7. Well, 8 mod 7 is just equal to 1. So this is saying in 7 days, it will be the day called 1 again. If I ask what day will it be in 3 days, and it's currently Monday, I can do 1 plus 3, and then that's going to be, and I calculate mod 7, and that's just going to be equal to 4, right? If I do 4 modulo 7, 4 is equal to 0 times 7 plus 4, and this coincides with what you actually think. In 3 days, if we're starting on Monday, which is day 1, then it'll be day 4, namely Thursday. So I'm telling you that computing days of the week or putting the days of the week in correspondence with the class of remainders modulo 7 means that I can calculate which day of the week it'll be in any given number of days. Does that kind of help, Morgan? Yeah, I think it's much easier to think about smaller examples first. You think, okay, I'm on day 3, it's Wednesday. What is 3 plus 10? What day will it be 10 days from now? Well, this is 13. I'm trying to calculate 13 mod 7. Well, this 13 is equal to 1 times 7 plus 6. So if that's correct, yeah. So in 10 days, it'll be Saturday. And that makes a lot of sense because every copy of 7 is a full week. So you end up in the same place, right? 13 being 7 plus 6 means that yeah. Sorry, yeah, if I add 10 days. I do a full week, and then I add an additional 6 days. So I end up on the 6th day. Feels a little sketchy, but okay. This is at least some motivation for why we would care about this kind of process of taking remainders. Okay, so the next step that we do is we set up the following. So definition. This is a new symbol. This is called congruence. A is congruent to B for A and B integers. And we write it A congruent to B mod M if M divides A minus B. Okay. So what I want to kind of give as a warning, there are now 2 notations flying around. One is the form A mod M is equal to B. And here, this is the function picture. So remember here, mod M is a function taking you from Z to 1 or 0, 1, 2, all the way up to M minus 1. And so this notation, A mod M is equal to B, says I take a number A, which is any integer, and then I pick up its remainder mod M, and that's going to be equal to B. So this is one notation and one concept. Here's a second concept. A is congruent to B mod M. And this is the definition that I just gave you. The mod M is in parentheses just for ease of writing, so that you can keep track of what the modulus is, like what M is, and then what the other numbers flying around are. It's really just notation. I'll try to hold on to it as often as I can. The book puts things in bold, but I can't write in bold. So this is an equivalence relation. I haven't defined an equivalence relation yet, but we'll get to those pretty soon. And it can either be true or false. We also write A is not congruent to B mod M if M does not divide A minus B. I'm about to do an example which will hopefully clear up what's going on. But currently, just with this definition and these examples, does anyone have any questions? Okay, let's look at things mod 7. So let's examine congruence mod 7. So I'm going to do my number line. I'm going to start off with 0. So I'm going to write down part of the number line. 1, 2, 3, 4, 5, 6. Wow, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 maybe. And then I'm going to do some negatives. -1, -2, -3, -4, -5, -6, -7. Great, a number line. We're going back to your earliest mathematical days. Okay, so my first question is, What are all the numbers, or what are some numbers which are congruent to 0 mod 7? So A congruent to 0 mod 7. Yeah, exactly. 7 and 14 are two examples of numbers that are congruent to 0 mod 7. 7 and 14 work because the definition of congruence says M must divide A minus B. And indeed, 7 divides 7 minus 0, and 7 divides 14 minus 0. 7 also divides negative 7 minus 0, right? 7 divides negative 7. Oh, you can't see. So what I'm going to write here is A congruent to 0 mod 7. And then it's going to be a sequence of numbers 0, 7, 14, 21, all the multiples of 7, 28, and so on. And then negative 7, negative 14, negative 21. So what does it mean to be congruent to 0 mod 7? Yeah, exactly. Being congruent to 0 mod 7 is the same thing as being a multiple of 7. And you can read that straight from the definition. If A is congruent to 0 mod 7, that means 7 divides A minus 0, or 7 divides A. So any number in here is congruent to 0 mod 7. Okay, let's do 1. A congruent to 1 mod 7. Can someone tell me at least one number that is congruent to 1 mod 7? I'll do some work over here maybe. What's something that's congruent to 1 modulo 7? Yeah, 8 is going to work, right? Because if 8, let's check if 8 is congruent to 1 mod 7. What I'm asking is, does 7 divide 8 minus 1? And the answer is yeah, definitely. 7 divides 8 minus 1 because this is just saying 7 divides 7. So 8 is in here. So 1 is in here, 8 is in here. 15 is also in here because 7 divides 15 minus 1, right? 15 minus 1 is just the same as 14. So 15's in here. How about 22? Does 7 divide 22 minus 1? Yeah, okay. 22, 29, and so on and so forth. How about negative 6? Is negative 6 congruent to 1 mod 7? Yeah, because 7 divides negative 6 minus 1. 7 divides negative 7. Exactly. So you can think of the numbers that are congruent to 1 modulo 7 as multiples of 7 plus 1. That is a reasonable way to think about it. So negative 6, negative 13, negative 20, and so on and so forth. What about, let's do A congruent to 5, mod 7, sorry. Well, first of all, a number is always congruent to itself, modulo 7, right? So 5 is certainly congruent to 5 mod 7. Why is that? Right. Right. Yes. the definition that I was looking for here is that 7 divides 5 minus 5. 7 divides 0. Or in other words, I can write 0 as equal to 0 times 7. That is why 5 is congruent to 5 just by definition. Yeah, so it's helpful to note here a priori that the definition of congruence doesn't officially involve the division algorithm. It just implies examining, does the modulus divide the difference? Okay. So 5 is congruent to 5 modulo 7. What about, can someone give me another number that's congruent to 5 modulo 7? Yeah, 12, exactly. And I can check that. This is looking very much like scratch work. I hope this isn't too messy. But 12 is congruent to 5 modulo 7 because 7 divides 12 minus 5. 12 minus 5 is just 7, so 12 is in here. Also 19, because 19 minus 5 is 14. Also 26, also 33, etc. And then negative 2, right? I'm running out of space. Negative 2 is congruent to 5 modulo 7 because 7 divides negative 2 minus 5, which is equal to negative 7. Negative 2, negative 9, negative 16, etc. So we're kind of getting the feel for what things are congruent to each other, modulo 7. The things that are congruent to 0 are all the things that are some multiple of 7 away from 0. The things that are congruent to 3 modulo 7 are all the things that are distance 7 away, or a multiple of 7 away from 3. 1, 2, 3, 4, 5, 6. I could have computed that, but instead I just, counted. Does this start to make sense about what things are going to be congruent to each other modulo 7? Any questions on this big example that I just did here? Okay, so what I'm going to do next is I'm going to relate the two versions of mod. So, theorem. And I think, Catherine, this is essentially what you wrote, and which I then corrected, and which I will now uncorrect after this theorem. Let A and B be integers in Z, and let M be in Z greater than 0, so M is some positive integer. Then A is congruent to B mod M. Remember, this is the M divides the difference. If and only if A mod M is equal to B mod M. So here is the new definition of congruence, and here is the function that we apply onto the integers and use the division algorithm. Okay. So let's prove this. I have an if and only if statement. What am I going to need to do to prove an if and only if statement? Yeah, I need to prove both ways. So we first prove that A congruent to B modulo M will imply A mod M is equal to B mod M. Okay. So we assume that A is congruent to B modulo M. Since A is congruent to B modulo M, what do we know? If I assume A is congruent to B modulo M, we use the definition to say, yeah, we have M divides A minus B. And what does it mean if M divides A minus B? What does it mean to divide? So A minus B is equal to M times K for some integer K. Exactly. So we have this relationship, or in other words, A is equal to MK plus B, right? So now I'm going to use, I suppose, the division algorithm. Now, using the division algorithm on B, should I do the division algorithm on A or on B? I'm actually not sure. Let's find out. Using the division algorithm on B, we see B is equal to M times Q1 plus R1, where 0 is less than or equal to R1 and is less than M, right? This is what the division algorithm says I can do for any B. Moreover, if I write things out this way, what is B mod M? Yeah. So B mod M is equal to R1. So now we want to understand what A modulo M is. Now using the division algorithm on A is equal to MK plus B, we see A is equal to MK plus MQ1 plus R1, which is equal to M times K plus Q1 plus R1, where, again, 0 is less than or equal to R1 is less than M. Right? I just used the division algorithm in its full generality for B, just saying B must be able to be written as M times Q1 plus R1. And then I plugged in this B for my relationship on A. So now A is M times this new integer plus R1. Thus, what can I say about A mod M? A by the division algorithm is equal to M times some integer plus R1. Yeah, A mod M is also equal to R1, just by this expression. What mod does is you write your number in the division algorithm, namely M times an integer plus a remainder, and I did that for A, and its remainder was R1. But now I see that the remainder for A mod M is the same thing as the remainder for B mod M. Thus, A mod M is equal to B mod M. The other direction is easier, and so maybe I should do an example here. Let's do 51 is going to be congruent to, hang on, 16 modulo 7. And now what I want to show that 16 mod 7 is equal to 51 mod 7. So I'm just trying to do an actual example and plug in the proof to kind of so we can see what's going on. So if 16 is congruent to 51 mod 7, that means 7 divides 16 minus 51. Can someone tell me what 16 minus 51 is? Negative 35. Good. Indeed, 7 divides negative 35. 7 divides negative 35 because negative 35 is equal to negative 5 times 7. Okay. So what I did here is I wrote, so this is the proof. I'm kind of redoing what the proof is. The proof says if these two are congruent, then I rewrite 16 as being equal to mk plus b. So 16 is equal to something plus b. And that thing is going to be negative 5 times 7, right? 16 is equal to negative 35 plus 51. Oh, you can't see what I'm doing. This is my A is equal to mk plus b. Is that okay? Okay. So now the next question is, first I consider 51 mod 7. What's 51 mod 7? Well, that's the same thing as doing the division algorithm on 51. So 51 is equal to 7 times 7, which is 49, plus 2. So it's equal to 2, right? Now when I compute 16 mod 7, I use this expression and I say, well, 16 is equal to negative 5 times 7 plus 51. But 51 is equal to, so this whole thing is equal to negative 5 times 7 plus 7 times 7 plus 2. And I just factor out a 7 out of here. So it's equal to 7 times negative 5 plus 7 plus 2. So I'm retracing what the proof was within an example. First, I write A as equal to mk plus B. Then I just figure out whatever B modulo M is, right? It's this thing. And then I use these two expressions together to show that the remainder of 16, or of A modulo M, is exactly the same as the remainder of B modulo M, because all of the non-remainder part just gets lumped in with this divisibility part, like this. Did this example help? Okay, I hope so. I did it because I hoped it would help. Yeah, I think that probably if you do some examples and you work, those are the same, Alex. If and only if is the same as a by implication. So I only proved one direction, and technically to finish the proof, I'd need to do the other direction, but the other direction is much easier. Okay, it is 10:10. I've already held you too long. It's 10:11. I've held you a minute too long. But of course, if you have any questions, please feel free to ask me, and otherwise, have a nice Monday.
Thank you.
Yeah, sure. Hey, Janae, got any questions? I thought that was hell no. Okay, cool. I was recording. Great.